So last time we were talking about the case of complex eigenvectors, right? And we saw that what would happen is that you would end up with these complex solutions. It was pretty straightforward. Like if you had Z, if Z equals A plus BI was an eigenvalue, right? And C being U plus VI was a corresponding eigenvector. Then you ended up with complex value solutions, right? Xt being e to the at cosine bt u minus sine bt v plus I e at sine bt u plus cosine bt v was a solution, right? And so this was a complex value solution. Right? Here's the real part. Here's the imaginary part. Right? And that was, as we said, the end of the story, unless your matrix, right? So we're dealing with some system. Right? If your matrix were real valued, then whenever you have a complex eigenvalue, they occur in complex conjugate pairs, right? And so you would have E and EZ, and EZ conjugate would both be eigenspaces, and in fact they were conjugate spaces to each other, right? EZ conjugate was the same thing as EZ conjugate, right? You can say that in notation. EZ conjugate was the conjugate, right? And so what was good about that was that, well, if this was a solution, then its conjugate was a solution, right? In that case, if this is a solution, then its conjugate is a solution, and then you can add them together. When you add two things that are conjugates of each other, well, then you just get twice the real part, right? When you subtract guys that are conjugates of each other, well, you get 2I times the imaginary part. And so, so in the case that A is a real matrix, we get from the pair of conjugate eigenspaces, the pair of conjugate eigenspaces, we get two real value solutions, namely the real part and the imaginary part. Right? So we're going to call it R1t, e to the at cosine btu minus sine btv. One is just the imaginary part of this guy, e to the at sine btu plus cosine bt. Right? And that's pretty much where we finished up last time. Okay. Any questions on how that happened? You simply followed from the fact that if you have a real value matrix, then your characteristic polynomial had real coefficients, right? And so if you conjugate it, you get the same characteristic polynomial, right? So anything that satisfies the original characteristic polynomial, well, its conjugate will still be a root of that characteristic polynomial, right? If you have if you have that a naught plus a1z plus a n z equals 0, and let's say the ai's are all real, well then, when you conjugate the left side, you still get 0, right? But that's the same thing as saying that because these guys are real, when you conjugate them, nothing happens, right? So you get a naught, a1 z bar plus, sorry, this would be z to the n, plus a sub n z to the z bar to the n equals 0. And so what this says is that whenever z is a root of a real polynomial, well, z bar is going to be a root of the real polynomial, and vice versa. So that it's roots of real polynomials occur in conjugate pairs if they're complex, right? And so from there, everything else follows. Any questions about that? Aaron?
You said that when you added them together that you would get 2 times
Yeah.
the root, so why does that not appear in the...
Because I divide by 2.
Oh,
Right.
okay, so that's just arbitrary because you're going to multiply it by a constant.
You can multiply by any constant, right? It's a homogeneous equation,
Okay.
right?
So if whatever solving specific initial value problems, are we going to have to take into account for that too?
Well, that happens afterwards, right? So, I mean, you have these guys, and then you would figure out what linear combination of them gives you that satisfies those initial value conditions, right? So, I mean,
Okay, yeah, but you just multiply it.
yeah, you would just put constants on it, put the appropriate constants to satisfy those initial value conditions, right? You find out what linear combination of these two satisfies that. So, if you had some constant on it, well then,
Yeah.
you know, you would just compensate. Your coefficients would compensate.
Yeah.
In a lot of these equations, you end up getting an answer for your complex root that's like a plus or minus bi. So that's just like the root and the conjugate.
That's what we're saying, yes.
So it's basically just that we don't have to have like a conjugate for each one because like both of them are roots.
That's right. In some sense, you only need to do half the work, right? If you've got a real matrix, then you only need to figure out, the eigenspace for EZ. You don't really need to figure out the EZ bar, right? Because the pair of eigenspaces will give you this pair of solutions. So the pair of eigenspaces together, you get one complex solution from EZ. If you wanted to, you could do both. You could say, I'm going to get one complex solution from EZ. I'm going to get one complex solution from EZ bar. Well, if you choose cleverly, then the solutions you get will be conjugates of each other. Right? Will be conjugates of each other. And then you add them together, you subtract them from each other, and you get real solutions. Let me do an example.
Okay.
I think that's better than talking. Okay. So, example will be a little bit big. No, not that big. Okay, so here's the example. Suppose we have a pair of second order equations. So x1 double prime equals negative 2x1 plus x2. X2 double prime equals x1 times 2x2. So this is sort of, just for fun, we're not doing a fourth order equation, but a pair of second order equations. This will give us a 4x4. This will still give us a 4x4 system, right? So standard trick, right? You let y1 be x1, y2 be x1 prime, y3 be x2, y4 be x2 prime, right? And y2 being x2 prime means that y2 being x1 prime. Y2 is x1 prime. So, yes, sorry, I'm getting confused. Y1 prime equals y2, right? So y1 prime equals y2, right? Y2 prime, that's x1 double prime, so that's minus 2 y1 plus x2, that's y3. Right? Y3 prime is just x2 prime, that's y4, and y4 prime is x2 double prime, that's x1 minus 2 x2. Sorry. So that's the easy part. That should be the easy part. Okay. And so you see what we get. We get the matrix then is going to look like this. 0, 1, 0, 0, right? Y1 prime is y2, right? we get negative 2, 0, 1, 1, 0, right? We get 0, 0, 0, 1, and we get 1, 0, negative 2, 0. Right.
And you know where you got that from?
It's right here, right? Y1 prime is Y2, so if I write this Y1, Y2, Y3, Y4 in matrix, if I write it in matrix, right, Y1, Y2, Y3, Y4, right, what matrix do I want? Y1 has to be just Y2, so 0, 1, 0, 0, right, Y2. Y2 prime is negative 2y1, negative 2y1, and 1y3. Negative 2y1, 0 y2s, 1y3, and 0 y4. Right? Y3 prime is y4, and y4 prime is 1y1 minus 2y3. Right? So I just translated the system into matrix notation. Wait.
Isn't that not variable though, the determinant is 0? Does that matter? I don't know. I just see that the determinant is 0.
The determinant is 0.
Or is it 0? Or, I don't know, I just saw the diagonals were all 0. Never mind, sorry.
The determinant is not 0.
No.
It's actually 1.
Oh,
Okay.
yeah.
Yes. No, wait, negative. Sorry. Okay. So, in any case, what we want to do, of course, is to find the characteristic polynomial and the dimensions of the eigenspaces. So, does it matter? Let me think about later if it would matter if the determinant or not. Where is it? But let me just go on. Okay. So what do? Well, we want to find the eigenspaces, right? And so we take the characteristic polynomial. I'm not going to expose you to the characteristic to that, but let me just write it down for you. It turns out to be x squared plus 1, x squared plus 3. Right? So you subtract off lambda on, you get lambdas, negative lambdas down the diagonal, and you take the determinant of that. It turns out to be this polynomial. And so you see what the eigenvalues are, right? The eigenvalues are plus or minus I and plus or minus root 3I. Everyone all right? This is nothing much is happening. Any questions? I shouldn't say nothing much is happening. Any questions? You all like obtain the blank look. I'm not sure if it's boredom or it's not. I admit it's not that exciting. So it's so maybe I shouldn't ridicule them for having such questions. Okay, so what happens next, of course, is that we need to find eigenspaces corresponding to these guys. But like we said, we don't need to do it for every eigenvector. We only need to do it for half of them, right? Because the other guys the other eigenspaces will just be conjugates of these eigenspaces, right? So you work it out, right? And you get that E sub I, right? That's the null space of A minus I. So you take this matrix and subtract i's down the diagonal, and then you would solve that system. It's just like solving a real system, except you have complex numbers. Okay, so it's basically the same thing. E sub I turns in, when you work it out, and I hope I didn't make any mistakes when I did this, but you will never know. Turns into the span of I, 1, I, negative 1. And E root 3I is the span of I and negative root 3, negative I, root 3. And like I said, you know, we don't really need to think about the other spaces because E minus I is just the span of the conjugate of this, right? So you just take all the imaginary parts and put minus signs on them. You reflect the imaginary parts. And okay, so and from EI and E minus I, we will get one pair of solutions, right? Right? So from E plus or minus I, we get one pair of solutions, right? That's R1 is going to be E to the AT. Well, A is 0, right? E to the 0t. Cosine B is 1, right? Cosine T times U is the real part of the complex eigenvector, right? So that's 0, 1, 0, negative 1. Right, minus sine t v is the imaginary part, well that's 1, 0, 1, 0. Right? Right. So that's one of our solutions. Right? And the other guy, R2, is going to be the other thing here. Right? So we get sine, of course, e to the 0t is just 1. So we don't really need that. Okay, so then we get sine of t times u, 0, 1, 0, negative 1, minus plus cosine of t times v, 1, 0, 1, 0. Okay, so this is our pair of real value solutions from the first pair of eigenspaces. Okay? And similarly, from the other pair, right, we're going to get, well, A again is 0. Here we're going to get cosine B, that's root 3t, times the real part of that. That's 0, root 3, 0, root, 0 minus root 3, 0, root 3, minus sine root 3t times the imaginary part. That's 1, 0, negative 1, 0. Okay. And let's call this R3. And we get also R4, which is sine root 3t 0 root 3 0 root 0 minus root 3 0 root 3 plus cosine t 1 0 negative 1 0. And those would be our 4 real value solutions. Yes.
Oh,
Just e to the at, where a is the real part of the complex eigenvalue, but our eigenvalues are pure imaginary, so there is no ER, there is no exponential. Okay. Geometrically, what do you see these things do? What are these things? In 4-dimensional space. You've got some vector, you've got some other vector, right? These vectors are perpendicular to each other, right? And you are fitting them with like cosine and minus sign. Well, think about what would happen in R2, right? If you had perpendicular vectors and you hit one guy with the cosine and the other guy with the sine,
The ball, isn't it?
it's going to be spinning around. Yeah, it'll be a circle. And in 4-dimensional space, it'll be the same thing. These two will determine some plane, right? And these things will just be spinning around, just spinning around in a cycle, right? They'll be spinning around in a cycle. I guess these guys are the same length. These guys are not the same length, so it'd be an ellipse, right? The same would be spinning around in some sort of ellipse, right? And just keep on going like this. Okay. if there were e to the at, if our eigenvalues had some coefficient, some real part to it, well, if the real part were positive, then what would happen? Well, as time went forwards, the magnitude would be right. It would become unbounded, right? These things would spin off as time goes on. These things would spin off towards infinity, right? And if you reversed time, they would spin inwards towards the origin, right? And vice versa, if this thing were negative, right, then as time goes forwards, they go into the origin, and you go time goes backwards, they spin up towards infinity, right? And so you see that the behavior, the qualitative behavior of these solutions, depends on very simple things, right? The sign of the real part, whether or not there exists an imaginary part, this sort of thing. Here,
Oh, I was gonna ask, is that like used to model like orbits or like other things like that?
yeah. Or so I think. So this is what I wanted to show you guys last time. Give me a minute. Hopefully this will work this time. While that thing is warming up, let me sort of write what I'm going to show you. If you look at 2x2 systems, right? 2x2 systems, the matrix looks like A, B, C, B, right? And then the characteristic polynomial, right? What is that? That's going to be A minus lambda, B minus lambda, minus BC, right? That is to say, lambda squared minus AD lambda plus AD minus BC, right? Which, if you want, is AD is the trace, right? So it should be A plus B. AD is the trace of the matrix, right? The trace of the matrix A plus B. The determinant, of course, is AD minus BC, right? That's this thing here, right? So this you can write as this, right? The characteristic polynomial, is determined by the trace and the determinant, right? If you've got two matrices with the same trace and same determinant, you're going to get the same solutions, right? And you see that the solutions are, right, t plus or minus root t squared minus 4b over 2 by the quadratic equation, right? And so this thing, t and d, what does this tell you? That t and d govern, right, the qualitative behavior, of the solutions, right? You see that, right, if t squared minus 4d is negative, then you get complex solutions. If t squared minus 4d is positive, you only get real solutions, right? And so, if you have a plane, the trace determinant plane, then your behavior depends on where you are. Depends on where you are with respect to a certain parabola, right? If you are right down here, t squared minus 4d is positive, right? So below the parabola, we have real solutions, and above the parabola, we have complex solutions, right? And if the trace is 0, right? If the trace is 0, that means that the real part of the eigenvalue is 0, right? And so we get this, at least above here, if we're on this part, then we get this you just get spinning around in circles, right? You get this sort of thing, right? Where the solutions spin around, but there's no change in magnitude, right? If t is positive, then you get the case where things spin out towards infinity, right? If t is negative, well then they're going to spin inwards towards the middle, right? And then here it sort of depends. Let's see if I can get this. So this is just for fun. I wouldn't worry too much about exactly. It's easy to work out the details if you feel like it. Okay? How your choice of T and D will play out here. So the good thing about being a professor is that publishers send you free books and free software, trying to get you to use their books. This is actually a pretty good book, so I'm starting to be swayed by it, particularly by the software. So this software allows you to just pick places. Like if I choose, say, like here, then you see that you get this sort of spinning, right? Things spin. That's the. I think you can click here. Yes. Okay. So these are like particular solutions. Right. So right, if I'm over here, right, you see what happens. Things spin out towards infinity. Right. If I'm over here, things spin inwards towards zero. Right. I think so. In your text, they talk about this a little bit, and they say they give these things names. Right. In this case, they call zero the center. Right. In this case, I think it's called a spiral source or something like that. Spiral source. In this case, a spiral sink. Right. Things are sinking in towards towards zero. Things are coming out of zero. Right. Down here, you have saddle point. You have what's called a saddle point. Right. So you've got here you've got one positive eigenvalue and one negative eigenvalue. Right. So but you've got one positive eigenvalue and one negative eigenvalue. So you see that along one of those, each of those lines corresponds to eigenvectors of that eigenvalue. Right? It's a solution. If you hit that solution, you just expand along that line. Right? Having real eigenvalues basically means that you have these linear solutions. Right? And you see that one of these guys, one of these guys has things flowing out from the origin, right? That's because one of the eigenvalues is positive, and then the other guy has things going into the origin because that guy's eigenvalue is negative, right? And so this is what is called saddle point in the book, right? And so over here. Right, this is the same thing, but so again, okay, so both of these guys now have positive eigenvalues. Both of these guys have positive eigenvalues, but one of them dominates over the other one, right? Because one is bigger than the other one. Right, so right, this one here is the dominating one. And so the things that we haven't done are what happens when you have repeated roots, right? What happens when the discriminant, right, when t squared equals 40, then you've got a repeated root, and in that case you've only got, maybe you've got only one eigenvector, only one eigenvalue, right? And if you're unlucky, maybe you don't get, you don't have enough eigenvector, you don't have a full basis of eigenvectors. Anyway, we'll get to that shortly. Yes, Dan?
Is this related to comic structures in some way?
To what?
To like comic structures, since like there's like ellipses and hyperbolas? Like, is this somehow related? Because like, I remember in high school, like, my teacher said something about like, if you like cut a cone up in different ways, you get the shapes. So is this related to like cones in some way?
I mean, I'm not sure. I don't think so. I don't think so, but but it could be. I don't really know.
In the book, for a couple of the problems that we were assigned, it asks you to draw the direction field.
Yes,
and
yes.
The solution as t goes to infinity.
Yes.
So, what do you want us to do for that? Because I'm not really sure.
So let me say, I think there you do it on the computer, I would say, but
How?
I think there are programs online. So I found, if you want, I can look for a program online.
Yeah, if you can send me
but it's,
because I'm just confused as to how to do it with the matrix notation. So you know how we have like, it'll be like E times, it's like the solution has vectors like in it, and I don't know how to do that on the program.
The program that you gave us at the beginning of the year doesn't.
that one's do it. Yeah, that's for single programs.
Yeah.
Yeah, but I think at the same website, there's another one that will do it for two buttons. But I'll look for it. You'll look kind of worried. When I was looking for something, before I found this, I found something else online that's basically the same thing, but this was better. But there's definitely online these sorts of
You
tools.
should maybe send this one.
Yes, yes. Okay, so, okay, that's all I wanted to show you. Turns on this. Okay. Okay, is everyone all right? Are you all tired? Are you tired? Why are you so lacking in energy? I guess it's
Class registration.
class registration. I know it's near the end of the term. Hang in there. This is usually the point where people run out of energy. Same thing for the professors. But you just keep on doing it. It's just like hell and Sisyphus. In fact, Sisyphus is a perfect analogy. Like every year you push the rock up, you try to get the students to the top, and then the next year comes and you have to start pushing the rock up.